values are on top here, and the y values are here. And the x are called, those words again, The x are called the explanatory variables, and the y's are called the response variables. So we're gonna look at how the relationship between two variables. And that makes a scatter plot, which just means you have a bunch of points scattered around. So we can approximate the scatter here to a straight line, and that's what we're trying to do with the regression. So we have these different forms here. I'll pull this down for a while. So I make it a little easier to see. So we talked about the positive, the ones that are in the positive direction, which is like we're talking about the slope of the line over here. So this is a positive slope, negative slope, no discernible direction here. Curves, you never run into this really. They can't, because it's all about a straight line, approximating a bunch of data points with a straight line. So we have these different descriptions we can talk about. So the direction, positive direction, negative direction, no direction. The form of the scatter plot. So this is straight. This kind of looks like a curve. And the strength, how closely do the points in the plot follow a straight line? So here, this seems like it's linear because it's a line, so it's a strong linear relationship. And we can tell how strong it is by figuring out the correlation coefficient, which we're getting to. And this is a weak linear relationship. So these look pretty good together. You're never gonna have it exact, but, because that won't be like a real life thing. Positively associated, so these are questions they'll ask, and there's two examples here, we might go over that. There's another scatter plot. Alright, the correlation coefficient is R. It tells you how closely the points that you have, the scatter plot, approximates a straight line. So the correlation R measures the strength and direction of a linear relationship between two quantitative variables. And quantitative means they're numbers. So remember all these long things on your equation sheet? This one's like just x1, y1. So we have x and y because we're doing a two-dimensional plot now. We have x data and y data. Remember that s of x and s of y are the standard deviations. So R is a complicated measurement, but this is how we know that we're going to do it by hand. So we're going to do it with our calculator. So here measuring linear association, continued. X bar, which is the mean of the x values. Y bar is the mean of the y values. For these points, x sub 1, y sub 1 is 1 point, x sub 2, y sub 2 is another point, all the way till however many you have. We know these things, those are the means. The standard deviation, this is what that ends up being. For each observation, x of 1, 2, and so forth, you take the summation of, as I goes from 1 to n, minus the mean square. And there's a 1 over n minus 1 there. So s of x is the square root of this. And s of y is the square root of that, which we're going to see in our, when we do it on the calculator, which is kind of really nice. I think we did this. 11. Calculate the correlation for the following data. I mean, we can just do this one again. I feel like we maybe did this one already. It must be in warm-up. There's one this morning too. All right, let's see if we, let's just do this one. I think we did it. We'll do it on a calculator just to get us all warmed up here. And I'll just put that up there. Okay, so we have these points. I'm pretty sure we did this before, but it's really quick. It's only 3 points. So this one is a x of 1, y we'll just find it first. So let's do it together then. Does anybody need one of these calculators? I have extras. This is always the one I'm gonna use, so otherwise it gets too confusing. If you have a calculator that you like and you wanna learn how to do all this stuff with it, they're all available on that part of the handouts for the class, right? They have those pictures of the calculators and exactly how you enter the data for it. So you can pick a different calculator if that's what you're using, but I can't go through all the calculators, I'm gonna drive myself crazy. So I'm sticking with this one. Okay, so we want R, which is the correlation coefficient. I know it's kind of a complicated name. So we're gonna, we start by going to stat, second function stat, and it's two variable, can't really see what I'm doing, but we have to put the little arrow to two variable, and then we'll just say enter, and then we go to data, now we look at the data. So it says x1 equals something, and so we're gonna put 1, and then put a down arrow. So if you already have data in there, just write over it. Just put a different number in it, it'll handle it. y1 is 1, so x1 is 1, sorry. And then we have y1, this is asking for next. y1 is 2, so I actually put, so I just put a 2 in there right now. And then we do the down arrow. So we got this one done. So now we want x2. So this is 2. And then down arrow. y2 is 3. So y2 is 3. And then we do the down arrow. And then we have x3. Letter x3 equals 3. So we put a 3. And then we do the down arrow. And then we have y3. And that's 7. We put a 7 and do the down arrow one more time. And we don't answer, we don't want any data here. So we have x4 equals nothing. So just hovers on that. Alright, so now we've got the data in. I can finish this. 3 and 7. So now that's the fun part. So now we get the key stat there, statistic variable, and it's going to calculate, and it's going to give us all this stuff there. So we just push that button, it says calculating. And what we've got the number of elements there are, the n is equal to 3. So they'll have a whole bunch of things across the top here. So n is the number of points you have. So if it's underlined, then that 3 goes with the n. And then we move it over to the next variable, and that's the mean of the x values, and it says that's 2. And then we move it over to the next one, the standard deviation in the x direction, and that is 1. That seems kind of weird, that's all right. And then we keep going for a while, because we want to come to, we don't want to do sigma x. Sigma sub x, we don't do that one, so not yet. So we move over, and then we get to y bar. So y, the mean in the y direction is 4. And then we got the standard deviation in the y direction, and that is 2.645. No, it's decimal places. I just put it. And then r is going to be way at the end. So then we do the right arrow and skip over the sigma y and summation x, and just keep going. Keep going, don't give up hope. R. So we get that R is the last thing they tell us. 0.945. That's the R, and that's the last one. Before the R, there's an A and a B, and that has to do with the regression line. That's what we're going to look at for today. So anyway, that's our correlation coefficient. So I'm going to put that somewhere for this data, just so we can remember it as we go through this PowerPoint. 0.945. So the R can either, in absolute value, it could be 1, which is perfect, or close to 0. So it's always like 0.9 is like a really good strong correlation, because that's a correlation coefficient, between x and y. Or you could say between the explanatory variable and the response variable. Okay, so that's what it means. So we found it, and it wasn't too painful. And then here they're going to talk about so let's get rid of all this crazy writing here. Okay. Correlation makes no distinction between explanatory and response. We're just correlated or not. R, it doesn't really tell you anything about those two. We just know that we have a strong relationship between the two. R has no units and does not change when we change the units of measurement of x, y, or both. So if you change the units, like something's in feet and something's something in temperature or something, it has no units anyway. So R is just R. Positive R indicates positive association between the variables, and negative R indicates a negative association. We already showed those graphs back. This would be a negative slope, and this is a positive slope. The correlation R is always a number between -1 and 1. If R is close to 0, we have a weak linear relationship. If R is close to -1 or 1, we have a strong linear relationship. Either it's a negatively related or positively related. So those are the things that R is telling you. So let's look at that a little bit deeper. Oops, all right, so here is a scatter plot here. It looks like it's got a strong linear relationship, and it looks like it's positive, so it's going like this. And you can kind of picture a line being in here. So these are some data they took. Let's see what else we got. This example, storms predicted for your explanatory, and storms observed. So they don't seem to line up very well. I mean, it's positive, but I would say the R is going to be kind of weak on that, because they're not really tightly together. But that's kind of subjective anyway, so. That there is really not correlated at all. So that is a very low correlation coefficient, something like 0.1 or 0.2 or something. This one also, there's no you can't tell what direction you can't really see the straight line in that at all. So low R. Correlation requires that both variables be quantitative, meaning they're both numbers. And correlation does not describe curved relationships at all between variables, no matter how strong the relationship is. Because it always has to do with a straight line. So no curves. Correlation is not resistance. R is strongly affected by a few outlying observations. So that means that it is not resistant to outliers. It'll kind of go along for the ride. And we have a slide that talks about that.
So if we have a curved graph, does R just not matter at all?
Yeah, it'll probably just be really low. That's probably what happens, because it doesn't.
There's not a specific algebraic expression that describes the correlation between a curved graph.
Yeah, well, the curve. See, we're not really. We're looking at lines, so it's called a regression line. So curve isn't really a line. So that's off the line. So
yeah, but there isn't an R variable that would say the correlation between just x squared.
Well, it doesn't calculate that. It just calculates straight lines. That's all we're doing. I don't know. I'm not explaining it very well. I'm sorry. But yeah, you could think that you could fit a parabola to some data or something we're doing with this stuff, it can just deal with straight lines. It's called regression line. So it has to be a linear relationship. And a curve is not a linear relationship. So I mean, you could calculate what R would be, I just think it would be really low, and it wouldn't really mean anything.
Well, yeah, just,
So, yeah, so, don't, yeah, if you see a curve, just, I don't know, R does not really apply in that case. Let's see. It's not described because no matter how strong a relationship, how strong you think it is, I don't even know how you would say it's strong, if it's curved. Now wait, this line down here, just memorize these words, okay? Correlation does not imply causation. This is very much words to live by, and you'll be asked this question a lot of times. Like, what does that mean if R is so high? Does it mean that stuff on the x-axis causes the stuff on the y-axis? It's possible, but you can't say anything about it just by knowing what R is. So, we always say that if you think things are correlated strongly, you have a strong an R of like 0.94 like we do, it still does not tell you that the x data causes the y data. It just says they're correlated. So they could be totally different things, and they just end up being matching up with each other. So a lot of people are do studies to try to prove what causes what. But just because something's correlated doesn't mean that the x values cause the y values. So it's kind of a hard thing to think about, but just remember that line. Okay, so this is kind of what they're talking about here. Correlation does not imply causation. It doesn't mean that something caused something. And here's an example of what people might think something causes something. Example, ice cream sales are positively and strongly associated with homicides in big cities. Okay, so that means that, like, it seems so ridiculous, okay, so we sold all this ice cream at this little stand today, and guess what? There are all these murders today, too. This does not mean that an increase in ice cream sales causes more homicides. Even though the R might be large, there could be what's called a lurking variable. So the lurking variable kind of messes you up on that whole idea. It is a variable that is not among the explanatory or response variables, yet it influences the relationship among those variables. The lurking variable here, and it's fun to try to figure it out, because that's another question somewhere. I don't know if it's on the exam or probably on the quiz somewhere. And it's like you have to really kind of think about it too. It's kind of hard to think about it really. But the lurking variable here is hot weather. And then you're like, well, yeah, right? That makes sense, doesn't it? It doesn't mean that ice cream sales increases homicides. It's just that it's hot out, right? So there's a lot of ice cream sales, and there's a lot of homicides because it's summer. Everyone's too hot and crazy or something. But they both are influenced. Both of these things, the ice cream sales and the homicides, are influenced by this lurking variable that's not even part of this relationship. So it's just influenced because it's hot out. Not whether people are out. You can watch Law and Order and see if it's hot out or not. If there's more homicides. Causation is stronger than correlation. So causation is really that's really what we want. We want to figure out what causes stuff. But it's stronger to figure out causation than just with correlation. For instance, working out causes the amount of calories that are burned to go up. So that is actually a true thing. So how much you work out causes, so that's a causing thing, the amount of calories that are burned to go up. So if you exercise a lot, you're burning more calories. So those two things are related in that way. That's a causation thing. But if you just were given data and it was correlated, you couldn't really assume that it caused it. You have to have some other kind of, you have to look for lurking variables or have some other thing to substantiate that it causes it. Because that's really not what you're doing. We're just saying, yeah, they're correlated. They're gonna run together, you know? So be careful about that stuff. Well, we're not going to calculate R by hand anymore. Then use a stat button to double check. Well, you could do this. I mean, I was having us do this one seems way longer, cause you really gotta keep track of all those X's and Y's. But we could just do this little guy here, over here, just to get us more used to it again. And, yeah, let's just do this again. So find they want you to just compare. And to do this by hand, you just have to use your, equation sheet. Let me make sure everyone has an equation sheet. Does anybody need this equation sheet yet? You guys have it. Alright, you're gonna have to use this while you do stuff, because we have the, equation sheet for the 30x2s calculator, and then we have for any other calculator. So, they're both written here. So anyway, we'll talk about that when the time comes. Okay, so this is some data they give you later. Why don't we just wait till it comes? Yeah, we won't do this now because this very data comes up on the next slide. So we'll just move ahead. Alright, so now we need to do some type of back. And then actually, year 2, this doesn't have anything to do with what we were talking about, but your quiz 1, when I make sure I have them all and grade them, I will publish this, which has a solution, so you can see how to do it. The actual solution, so the way you work it out. So that was always helpful for studying for the test. So we're past chapter 4, and then here they talk about these things. And then chapter 5 is the regression line. This is a smaller version. You're lucky I made some of these smaller, these PowerPoints smaller than they used to be. Okay, so this guy, regression. Chapter 5 is on regression. A little more about it. Alright, so a regression line is a straight line that describes how a response variable y changes as an explanatory variable x changes. Okay, so that's what it's going to do. The regression line, and notice it's a line, is used to predict the value of y for a given value of x, when we believe the relationship between y and x is linear. Okay. So, this is just an example. I mean, they have these so bizarre examples, but this NEA, I don't even know if we want to really go through it very much, but this is the x-axis. NEA is something, I forgot, non-exercise activity, which I don't really know what that means, just maybe eating less or something. But that's the x-axis here, which is the explanatory variable, and then the y-axis here is a measurement of fat gain. So we just have these points. So we just have a bunch of data. So this is in calories, this is in kilograms, I think. So you got a bunch of points, and you just find the x and the y values, and you can just plot the points. Sometimes it's kind of painful because they're not really friendly numbers. But so we find a regression line, and we'll be doing that by hand. We'll be doing that to show you how to do it. We need you'll have a slope and a y-intercept, and then you probably need like a straight edge, or you can use like I found some white cards, you know, that kind of are hard up in the office. So I can bring those to you. I was looking for rulers, but I couldn't find any. Rulers are gone. I don't know. But anyway, you need to figure out like 2 points on this line, and then draw that straight line between them. So it's nice and straight. And you can see how the points surround it like this. So this line here, this is called the regression line, and it really, how it's figured out is it's the line in which the least amount of y movement on these, it's like, how do you say it? It tries to approximate the best place to put this, that's between an x value and a y value. I think that's talked about a little bit better in another slide, so let's just wait for that. Okay, so suppose that y is response variable, plot on the vertical axis, and that's the explanatory variable. Plot it on the horizontal axis. A straight line relating y to x has an equation of this form. Now, this is where we need the formula sheet. does anybody, everybody has this, right? Cause this is on the formula sheet. So y equals a plus bx is on this sheet, and this is the one that has the 30x dx. So a and b are in both the calculator, the general calculator here, and then our specific calculator. So we can say least squares regression, y hat, that little hat thing on it. So this is actually, this is the y values for the regression line. And least squares regression, y hat equals a plus bx. And a and b are also on your calculator. They come before the r does. But if you have a different calculator, they're different things. But what we did in class has to do, this is so confusing, I really hate that it's like this. What we're doing in class is based on this calculator, and that's the red right here. And the only difference really is just the a's and b's are reversed in our calculator as opposed to the book's calculator. Alright, so we've got all these other things it does here. A residual is y minus y hat, so you always want to refer to this so that you can figure out how to draw those lines. Alright. In this equation, b is a slope, so this is not our calculator. In our calculator, we have the a's and b's interchange, so we have b plus a. So this is the TI. So it's totally different, but it's just the a's and b's are reversed, right? So in this one, b is a slope, because it's of the form y equals mx plus b, remember that? So actually ours is a little bit better, because the b is like the y-intercept. But anyway, in this equation, b is a slope, the amount by which y changes when x increases by 1 unit. Or you could do rise over run to find the slope, and then go to another one, and then you have one line. Because you only need 2 points to make a line. The number a is the y-intercept, and the value of y when x equals 0. So it's where it crosses the y-axis. Okay, so that, and I won't get to do this, and then I think it'll be easier. Alright, this is the thing we were talking about before. Or somebody was talking about it, I guess I left it, I don't know how long I did it. Alright, this thing here, the least squares regression line of y on x is the line that makes the sum of the squares of the vertical distances of the data points from that line as small as possible. So here's the point here, this is a scatter point here. Observed response for this value for the x value if you go to minus 52. So if you go to minus 52 and go up here, there could be a data set. There's a data point that actually has this. So if I can see this, this is 3.0, that's on y. So this point here is minus 57, 3. Okay, so that is what that point is. And it says it's an observed point. So that means it's part of your data set. It's a number that's given to you. And then there could be another one for minus 57 that actually hits the line. That's a predicted value. Predicted by the regression line. So this is actually in the data. So it's observed. And then this one here, for minus 57, predicted by the regression line is right here, which is, I don't know, whatever, like 3.7. I'll call this like minus 57. Whatever that means, 3.7. Between 2.5 and 4. So this is predicted by the line.
What is the text saying?
What is what?
The text?
Predicted and
Oh, this is
observed.
observed?
No,
Okay.
the paragraph, above the graph.
Oh,
What is it talking about?
the least squares regression line of y on x is the line that makes the sum of the squares of the vertical distances of the data points from the line as small as possible. So we were just fitting a line here. So this is a point that's in the data set. This is is a point that's in your data set, this is a point that's in your data set. So this line that we get the slope and the y-intercept to makes the sum of the squares of these distances as small as possible. So it's like a computer program. It's like a
Oh, like squares that you.
yeah, so that the sum of the squares, so it's like this, you can think about it without the squaring part. But the squaring gets rid of the negative parts of it. So you have this length plus this length plus this length. There's a line that minimizes all those. So if the line was say it was like, I don't know, like this. This kind of line, that would really be minimizing it. Okay, so it has to kind of lie between all these points so that you can see that the vertical distances are not so far away. There won't be any big question about that. I mean, there's other statistics classes that really get into this kind of stuff, you know, and then you have to write a C++ program or something to make it figure that out. But you can never really do it by hand. So I'm just gonna slide on by that one there. But that's what you're doing. And then this is where you need your equation chart again. Equation formula chart. Because this is what the x be the explanatory variable is always is, and y be its response variable for n individuals. From the data, calculate the means, x bar and y bar, the standard deviations, sx and sy, and the correlation r. So this is all the things we're looking at here. And these are the things we do in the calculator. You can get that, you can get that, you can get that, you can get r. And then you can also get, the least squares regression line is this line. So you can get A and B also. All those things you can get from your calculator. So you can write this line. So there's the equation of the line, the least squares regression line. And then it turns out that B, not on the TX calculator, but in the book's calculator, B, which is our, in this one is the slope, is r, there's our r again, s of y over s of x. So if you didn't have this B, and you weren't really sure, like maybe confused with the a's and b's, this, you don't really need this. You can just do r times sy over sx, and that would give it to you. Because you already have all these, right? And over here, you find the slope, a, for us, or the y-intercept, it's going to be y bar, which is the mean of y, minus b, which is right here, or right here, times x bar. So, if you have your equation sheet in front of you all the time, you'll be fine with this. But it is kind of, I know, it doesn't seem like it's really helpful. Alright, but we'll do some examples with it. Alright, y hat, back here, on this sheet. So y hat is b, well, we'll just use the book one because it's too confusing. So y hat is the regression line, and that is equal to a plus bx, not on our TI one, but from the book. So a is this number, and that you find from your calculator when you put the data in. You also can find b from your calculator, so you can write this as a straight line. So this is like the y-intercept plus or minus plus the negative slope times x. So this is the equation of a line. Equals b. It doesn't have to be plus m. Sorry, I did it wrong. I wanted to write it as just a slope intercept form actually. So it's really the y-intercept plus mx. So this is the slope. And this is the b. So you can write this, and this is the equation of a line. So you could like put in values for x, do this awful math here, and get what y hat is. So you could do that, you could say if x is 0, you would just get this number. then you could rise on your way to the other one. But we'll do this together, probably next time, I guess. And it won't seem so mysterious. So y hat is the predicted fat gain in that last line with X calories of non-exercise activity. So it is the equation of a straight line. So that's the kind of the main point of it. So maybe, don't think about it too deeply, but that's what it is. I think we should probably, I can't move my mouse here. It doesn't want to come over here. Go over here. There you go. All right. So here's a nice little picture of that. So here we have, this is an equation of a straight line. And so the predicted values and everything, so we have, this is, if you put a value of x of 400, which is here, then it would approximate to be about 2, which is 2.145. So if you're putting in 400 for x, because this is actually x, right? And this is what you get for the straight line. So if you plug in an x value of 400, this, and you go up to the line, you can figure out what the corresponding y value is. But the line, the regression line, is just an approximation. But it's a good one because it takes into account, making this line takes into account a line that fits this data pretty well. Because otherwise you're all over the place. So anyway, so you put in a value for x, you get a value for y. This is y. So that's what we're doing there. And then we just need to look at an example. So then we'll be better. This goes on and on, doesn't it? All right, calculate the least square. Let's see what we need to do here. I want to just do a simple one. Let's see. We can do this. Did we do this one? Maybe we didn't do this one. Okay. So let's just do this guy. And there's an example that's at the end of this that we'll do next time. The least square regression line for the example from chapter 4, where we have this data, calculating the least squares regression line. All right, so we could do that. So what we're going to need is R and A and B. I don't know if that's not the same as that one, I don't think. I don't recognize the numbers anymore. Well, let's just put them in. Second function step. Maybe it did. Let's see, what do they, they're not going to tell us. Second function step. And then we go to the right here, you can say clear data. I don't know if it really works that well, but it is clear. Then we want to go to stat again. And we're taking 2 variable, enter. And then we put the data. X1 is 1. Y1 is 2. X2 is 2. Y2 is 3. X3 is 3. Y3 is 7. And then we do the calculate. Stat error. Calculate it. And this 3 is a 3 points. X bar. Oh, I guess I'm going to write down the things. Equals 2. S. So we need to know these variables. And S is 1. I think we did do this one. The numbers start running together. Y bar is 4. SY is 2.64. This is the same one. I'll save us some trouble here. And you keep going to the right. It has A is 2.5. It has B is negative 0.1. No, negative 1. That's not 0.1. And then it has an R, which we did. R is 0.945. So we found all those things. So let's see, we're going to do it on the screen here. No, do here, put that on timeline. I guess I'm just gonna save all the making of a regression line till next time, cause otherwise we'll get lost in it, okay? So we'll make a regression line and then we'll talk about it more, so it's more down the road. Alright, guys, that's kind of a tough section, I really always kind of worry about